Okay, so the last lecture, in the last lecture, we talked about the convergent of power series and the formal power series. And this lecture, we're going to relate them. Okay, so given two formal power series, we may form their formal product and formal sum. If f converges absolutely for some complex number z, we can substitute and give a value, and we call it fz, into this formal power series was substituted with z. Similarly for gz. And before that, we need a proposition from summation that should be included in first year calculus. Is that for any two absolutely convergent series, each term is defined as their Cauchy product, then this is absolutely convergent with the sum of the product. Okay? So this proposition will not be proved, and one should learn this in first year calculus or Calc 2, basically. So remark, with this proposition, we're going to use it with power series. So to the end, we said that we fix in z, and we may look at the series a and zn, b and zn, c and zn, right? And with cn is equal to this, okay? This cn is equal to this. And we can define alpha n as a and zn, beta n, and gamma n. Then gamma n will be equal to this, and each cn we substituted with this. But remember, zn is equal to z of k times z of n minus k for all k runs from 1 to n, right? So what we can do is that we can actually boil this inside, bring it into the summation, and this actually just turns out to be, this should be beta of n minus k. It's a typo here. Okay, let me write this. Should be n minus k. N minus k. Okay. Okay. Alpha k, beta n minus k. Right? So with that being said, if alpha n is this power series, beta n is another power series, both converges absolutely, then we have this power series, right, which is alpha gamma n, which is equal to this, right? Exactly what we have here, because each gamma n is equal to this, right? So this equality holds, and each alpha n is equal to this times this. So this power series equal to this power series times this power series, if we have convergence, right? So now we can finally start proving a theorem. It says that if f and g are two formal power series whose radii convergence are all at least r, then we form their formal sum and formal product. Then the series S and P again also have radii convergence greater than or equal to r. And for numbers that is inside this, right, we have f of g substituted with z. So which means that this formal power series substitute with z is equal to fz plus gz. And their formal product substituted with z is equal to fz times gz. Okay? So what this means that we can view this in terms of if we have the mapping, let's say phi, that takes a power series, the set of formal power series to C is a ring homomorphism. Right, with this being said, that sends f to f of z, right? So this is what it means. So to prove the product, we prove the product first. So we have those. Now we define dn is the sum of their absolute values, dn, then we have Cn less than or equal to dn by triangle inequality, right? Because this is less than or equal to the sum of those, right? And we know that for S less than R, we have this is true. Why? Because A n Sn and B n Sn, when S is less than R, these two sum converges absolutely, and dn is equal to this. So d, by the remark, right, dn Sn should converge to this product, which means that for Z with its norm less than or equal to S, we have that this, so we scale it by this, and again less than or equal to this because each C and dn are less than or equal to dn, and dn is actually equal to this, right? Which shows that this converges, but S is arbitrary, so the product P, right? P converges for all Z less than R, right? P is the product, right? Because we already have absolute convergence, then it implies convergent, right? For addition is even easier. We just simply by triangle inequality, right? That we can do this, and then we can split because each limit exists, they converge, so each limit exists. And because Z is less than or equal to S, the norm Z, right? So we have this. And SZ is equal to FZ plus GZ because this, right? And also P is equals to FZ times GZ because, right? I mean, we already proved it here, right? We already proved it here. Like what we did is that we already proved it here, right? So, yeah. Okay. So a formal power series determines the function of disk of absolute convergence. Is that given the disk, it sends Z to FZ. Okay, it sends Z to FZ. So we can raise the question, if two formal power series give rise to the same function on some neighborhood, are they equal as formal power series? So this says that two power series, if they agree, right, on the set, should all their coefficients be the same? Subtracting G from Z is the amount asking if a power series depends on a zero function on some disk center at the origin. Is this zero series? All the coefficients are equal to 0? Before we answer this question, we need a supporting theorem. It says that for a non-constant power series having non-zero radius convergence such that F0 is 0, so the constant term should be 0, right? This means that the constant term should be 0. Then there exists S such that it is around the disk for Z, norm Z less than or equal to X, it doesn't vanish. And Z is not equal to 0, right? Because we assume this, right? Okay, so to prove this, because it says it's a non-constant power series, but F0 is 0, so the constant term should be 0, right? So we can write it as this plus higher terms, which can be rewritten as this, right? So, you can rewrite it as this. AMZN multiplied by 1 plus HZ, where HZ is another power series, right? Well, for Z is non-zero, they're a scalar multiple of each other. Thus, they converges if and only if the other one converges, which means that this has a non-zero radius of convergence. Thus, it converges absolutely and uniformly for all Z less than or equal to R, right? Where R is the radius of convergence of F, right? For some, I mean at least, right? For some R positive, because it is uniform convergence, it is a continuous function for z less than equal to r. Hence, what we can do is that it is continuous, right? Because h0 is 0 and is continuous on this disk, which means that we can pick an s such that, like, right, this is like r, and we can pick an s here such that in between this gives hz minus 0. h0, right, is very, very small, which makes that 1 plus hz is non-zero, right? Which means that in this disk, 1 plus hz non-zero. Also, this is non-zero, which means that fz is non-zero, right? Because fz is just a product of these two, right? And we're done. Okay. Now we can answer our question. If f and g are two power series convergent, and there is a subset of C such that the set consists of the elements such that f and g are equal, okay? And the set E is infinite, and 0 is the limit point of E. Then f and g are the same, which means that all the coefficients are the same, okay? So we just let ht define as their difference, right? So it is a non-constant power series. If it's a non-constant power series, because f and g are convergent power series, h has non-zero radius of convergence, right? Because this is like a linear combination, right? f plus like negative g. Well, negative g is not the power series of non-zero convergent, right? Because scalar doesn't matter, doesn't affect the radius of convergence, right? So h has a non-zero radius of convergence. Also, we need h0 is equal to 0. Why? Because if we can pick a sequence in E such that it converges to 0, because we're given that 0 is the limit point, right? So we can pick a sequence in E such that xn goes to 0. But it has a non-zero radius of convergence, which means that it is continuous, right, in some disk. So by the continuity of h near 0, we have this sequential characterization of continuity, right? But because xn is a sequence in E, so this is like n0 for all n, right? So h0 must be 0, right? The sequence of 0 converges to 0, so h0 is 0, right? So we have proved that h0 is 0. Now, so we have that theorem 4.2.16. Where is 2.4.2.16? 4.2.16. I think it's the wait. Is it not? Is it issue in numbering? Wait a second. Oh, I think it's just this theorem. I forgot to change numbering. Okay, so we have that h is a non-constant power series, and h0 is 0, right? ft is a non-constant power series, non-zero radius convergence, f0 is 0, a0 is 0. Then there exists a disk such that, except at the origin, it doesn't vanish at all, right? So we have that this applies 0 is the isolated point of E, right? 0 is the isolated point of E because we can found a neighborhood of 0 such that it does not intersect E, right? Hz is not equal to 0, right? Because E is the set of all z such that fz is equal to gz, which is equivalent to hz equal to 0, right? Now, we have that h is the limit point of E. And because h is a non-constant polynomial, non-zero radius convergence, h0 is 0, we applied this theorem. We say that there's a neighborhood of around 0 such that other than 0 itself, it does not intersect E, right? Hz is non-zero, right? So which means that 0 is an isolated point of E, but 0 is also the limit point of E, which is a contradiction, which means that ht must be a constant polynomial, right? It must be a constant polynomial. But this constant must be 0 because E is infinite. If omega and 0 is not 0, then h of z is not 0 for all z, right? But we need hz is equal to 0 for some z because E is an infinite set, right? So ht must be the 0 power series. Okay? So here's an example. There exists at most one convergent power series, such that for some interval is equal to e to the x for all x in this interval. We showed, okay, what we say here is that if it exists, it must be unique, but we haven't proved the existence yet, okay? Because if there's another gx, fx, they equal on this interval, they're agreeing on an infinite set with 0 as a limit point, right? So by the result we've established that gt must be equal to ft, okay? So now here comes the lecture of combinatorics. We're gonna turn our attention to substitution of power series. This is gonna be long, okay? So suppose that this power series converges, then this also converges such that with a limit this is equal to this, okay? If each an is a real number and z is positive, the result still holds. So this thing here might just look intuitive, right? Well, I just choose to prove it for sake of completion, right? So let's suppose that is non-zero. Then we have the partial sum, and of Sn we have the partial sum of this. We denote it as Tn. Then Tn and Zn, Tn and Sn, they're related by Sn over Z, right? So by the limit rules in C, right? Because this converges, right? So S and Z converges as limit goes to infinity because Z is right. Z and N are independent, and we know that this converges, which means the Sn converges. So this holds, right? And we can move the scalar multiple outside, right? Which is equal to this is equal to 1 over z times this, and we move the z over there, gives the result. So here comes the substitution of power series. So given a power series f and a power series th, such that the constant term is 0, if the radii of convergence of f and h are non-zero, then the radius of convergence of their composition is also non-zero. Okay? Assume that fz is absolutely convergence for some, right? Because it's non-zero radius convergence, right? So suppose that it converges absolutely for all norm z less than r, with r positive, then and s is a number such that this is true. Okay, look at this. This is true, where s. Okay, then g converges absolutely with z norm z less than equal to x, and that for such z we have this holds, which is the composition of those two is another power series, and this power series is equal to f of h of z, where h of z is a complex number. So right, and f is so f substitute with h of z, a complex number, and this is actually equal to f of h, this composition power series substituted with z. Okay, so this looks obviously true, but the meaning behind it, you must be careful. We must prove such s exists because it's just the statement just said that and s is such that it's true, but we just prove the existence of s, okay? Because the radius of convergence h is also non-zero, then there exists a t naught such that converges absolutely, right? Converges absolutely. Then by the proposition which is proved, which is this, okay, it is not 4.2.19. Let me just erase this. Okay. Okay. Then we can move the t naught outside, and this is n minus 1, right? And we define this quantity equals to m. Now we leave the t naught fixed, and for any t that is less than t naught, we have this is true, right? Which means that this with t, which is equal to t times this, which is less than equal to what? T times m, right? But Tm goes to 0 as t goes to 0, right? So if we let t goes to 0, this goes to 0, this goes to 0, right? So the thing in the middle must goes to 0, which means that the limit of t goes to 0 of this thing is equal to 0, which means that we can find an s positive such that this is less than or equal to r, right? Because r is positive, right? If it already goes to 0, right? If you just let epsilon equals to r, right? So such s exists, which means that it follows that an of this is converges, because this whole thing here, this quantity is less than or equal to r, right? So an of x is less than or equal to r, right? Norm of x is less than or equal to r, but anyways, right? Then an of x n converges, because we assume that it converges absolutely for all, right? Okay, so we prove this is converging for some s. And now we want to prove the equality, and the equality is kind of brute force. So we consider the composition power series, whose nth coefficient is the nth coefficient of this, right? Now, we want to find an explicit formula for Cm, which is just define a set of numbers for all positive integers nm, such that we define dnm. So maybe you read this, is the sequence of all k1, kn, such that it adds up to m, and each of them are greater than or equal to 1. So we must, to make for this to make sense, we need m is less than or equal to m, right? Because we have n numbers, each is greater than or equal to 1, that equals to m, right? And b are the coefficients of h, okay? Those are the coefficients of h, okay? And if n is greater than m, we just define this as equal to 0, okay? So for m is greater than or equal to 1, and this, the coefficient of tm and ht to the power of n, so ht multiplied with itself n times, okay, is actually equal to this, which is dnm, right? Coefficients of tm and ht to the power of n, right? So this n, this little n, means that there are like n of the indices to the power tm, right, to the m, right? So this is what we have. So this comes from the formula of multiplication with itself, right? The formal product of power series, right? It just follows by that, right? So, which means that Cm is equal to sum from n to 1 to infinity, because eventually it should be equal to 0, so it's actually to m, right? An of, right, a1, a0, a1, an, this should be am, right? AMHM, right? Yes. So from right? You get the idea, A1H to AMHM, so A1 of the mth coefficient, right, which is this. So Cm is actually equal to this, okay? If I want to infinity dnm. Okay. Thus we have f of h of t is just equal to a0 plus Cm, this whole thing here is just equal to Cm, right? Exactly what I say here. So this is CMTM, A0 plus m from 1 to infinity, right? CMTM. So this is the expression of f of h of t. And well, we want to compute this, right? F of h of z is equal to a naught plus an, and each an, the thing inside is bmzm, right? The power n. So what does this equal to? F of h of z, right? Well, since we're assuming this is true, so it converges absolutely. So by our results on multiplication of power series, we use that, right? So this thing, right, is equal to this thing. Multiply with itself n times, right? Notice the n here and the n here, right? And multiply with itself n times, right? Because this is the series, right? M from n, right? M must be at least n, right? M must be at least n, right? This is the Cauchy product of this power series with itself n times, and this thing here, Zm, this converges to this would multiply with itself n times, right? We just use this result. What happens is that we're essentially using this result. Right? We use it multiple times, right? So we have, this is an of this n, but this thing inside is just dmn, right? Dmn. Oh, should be dnm. Okay. Yeah, this is a hard thing of writing such proof, right? Just keep track of your numbers, right? Your dummy variables. There's too many dummy variables. So we just substitute this. We substitute this thing as this, right? Which is dnm zm, and because this is the dummy variable is m, right? The dummy variable is this again dnm. All this should be dn m dn m. Okay. So yes, we move this into it, right? So, but remember, if n is greater than m, this is equal to 0, right? So m could actually start from 1, right? So the outside keeps the same, but this thing inside, m can actually runs from 1, right? Because before from here, like we have m is less than n, right? It's just 0, right? It only starts counting when m is equal to n plus 1. So before that, we're just adding 0. So the sum won't change, right? So we can continue this equality, okay? So now what we want to do is that we want to interchange these two sum. But to prove this, we need to show something about the absolute convergence of this, right? Otherwise, we cannot prove. We can switch the sum if this thing inside is absolutely convergent. So remember, we have this is true, right? Which is can be found up here. Exactly same thing, right? Recall we have, right? So we have this is true. Now, this converges absolutely, like obviously, right? This thing converges absolutely, right? So we can use our results on multiplication of series again, right? This thing will be equal to, right? This thing we can split to like some Cauchy product thing, expression, right? And each of them is greater than or equal to this, right? So here to here is just by triangle inequality and some argument about the limit and find the partial sums, right? The bounding things about partial sums, and we can take limit and still bound it and something like that, right? So you will fill the details. Okay. And this thing turns out to be an absolute value of d and m, right? Absolute value of d and m, right? So d and m because they're n numbers and they add up to m, okay? So, right, so from here, n starts from m to infinity, but we can start from 1, it doesn't matter, right? So which means that this thing, right, which is this thing, this double sum converges absolutely, so we can interchange, right? So, right, this thing here already converges absolutely, right? We showed this, right? Infinity greater than this, right? So we can interchange this. So we can change this to m, this to n, right? This to m, this to n. Well, which is just f of h substituted with z, right? F is just zn, right? Exactly the same. Phew, so we prove that this is true when... Okay, so this proof is kind of long. Yeah, it's all about counting, and the next one is also long. But before that, we need a remark, is that suppose denote the function send z hz by h check. We denote this by h check. Send z hz. Okay, define for this, and similarly denote the functions defined by series f and g by f check, g check, respectively. Then the relation, which is what we have here, is that gives g check is equal to f check of h check. So this is what the theorem actually means, okay? If we restrict ourselves to sufficiently small values of the variable, right? So this is about the composition, and last, we have about the inverses. So before that, with the same notation, we know that this is true, right? So this is really just 1 times this minus t times this, right? If we just work with like formal power series, this is just equal to this, which is equal to 1, okay? Equal to 1. And what if we substitute t? Each t is a power series. Each t is a power series. Well, does the equality still holds? The answer is yes. Okay, so if you just want to know the answer, well, the answer is yes. But if you want to show the proof, here's the proof. Okay. So we first calculate. So we want to compute 1 minus h plus 1 plus h squared plus da da da, right? So where f is this, so f of h ht f of h t is the power series 1 plus h squared plus h cubed plus dot dot dot. This is f of ht. So what we're doing is that we're calculating, so 1 minus h times this, right? So we first compute h times 1 plus h squared, right? And we also compare this with 1 plus h squared plus, and see what we can, if we do the subtraction, right? What does it equal to, right? So we first calculate this. And again, right? We have f of h and each cm is equal to, remember before we have an, right? But now all an is equal to 1 because this is how f is written, right? So it's just dnm, right? N numbers add up to m. Okay, so now it's correct. So then we have h multiplied by this, which is this multiplied by this, and which is by the distributive property of formal power series addition product, right? We can do the associativity, which is this plus these two multiplied together, right? The formal product, right? But each Sn should be something like this, the Cauchy product, right? Which is Ci Bni, right? From to n minus 1, right? And each Ci, just substitute each Ci to this, right? Should be Dni, right? Ci, I, right? So from 1 to I, Dni times b of n minus I. And maybe you can take a look at this and recall the definition of dni. So we have this equality holds, okay? So, and 60% of the proof is explaining why this holds, right? And here is the text. So maybe I'm tired of this. So probably you should take a look at yourself, right? Maybe take a look at this. Right? So the equality holds, okay? The equality holds. So now recall that we have f of h of t is equal to this, right? So this, if we just do this, subtract 1, which is this, right? This minus this, so which is this thing, minus h times f of h, which is this plus this, right? H times f of h. H times f of h, which is this plus s and tn, right? This plus s and tn. And then we just expand this. We expand everything. So this cm turns out to be, right, 1 to m, and this Sn is dkn, right? And starts from 2, right? The dummy variable doesn't matter, right? So we have the sum of this. And notice that this is a formal power series. It's a formal subtraction. Formal, okay? Remember. So remember that when m is equal to 1, right? These two there's a cancellation when m and n are equal to 1, right? So this actually starts from 2 and this starts from 2 because this subtraction here cancels them out. So this starts from 2, right, into k2. And we can just change all the dummy variables to m, right? Because they're dummy variables, right? So if this changes to m, then this thing also changes to m, right? So we just change our dummy variables all to m. It will look like this. Now, because this is like a formal one, sorry, so we can just fix m and we discuss about each of those, right? And we have the mth coefficient is this ugly power series. This is the coefficient of the mth coefficient, right? This one, and this one. But notice that we leave the 1 and it starts from 2 to m. And now we also have 2 to m. So these two cancels out, right? No matter what that is. And this will equal to d1m, right? Remember the definition of d, right? 1m, which means that only d1m, there's only bm satisfies this property, right? One number that adds up to m, which is bm itself, right? Tm, which is equal to 0. So we see that this thing is equal to 0. Is equal to this, equal to this, equal to this, equal to this, and is equal to 0. 0 power series. Right, so we show that this is a 0 power series. F of h minus 1 minus h times f of h. F of h minus 1 minus h times is 0. So we can rearrange this, which is f of h minus 1 equals to a times f of h. And we swap this, right? This is equal to 1. And this is just 1. 1 minus h times f of h is equal to 1. But f is equal to this, so we're done, right? Okay, so we have verified this is actually true. Thus, we have this final theorem. It says that if f with non-zero constant term, non-zero radius convergence, then the inverse such that gf is equal to 1 also has non-zero radius of convergence. So if you have inverse, then if you have inverse, then the inverse also has a non-zero convergence, provided that you have non-zero radius of convergence. So by multiplying constant to make a not equal to 1, and we can write ft as equal to 1 minus ht, with h0 is 0. So 0 constant term, right? The radius of convergence is mu f, and also h itself still non-zero, right? Which means that, also that the radius convergence of this is 1, right? By our knowledge of geometric series, yes, right? Which is non-zero. Which means that by by the results of composition, right? This series has the radius convergence non-zero, and the h is also non-zero, which means that this composition has non-zero radius of convergence. But by the remark, this thing is the inverse of 1 minus h, which is the inverse of f. So this inverse of f has a non-zero radius of convergence. So this thing is equal to g. So we're done. Right, we're done. Oof. Okay, so this is really a counting lecture, not complex analysis that much. But yes, so yeah, that's it for today, and I'll see you guys next time. Next time we're going to talk about analytic functions. Okay.